Alright, hello everybody, hello from your favorite artist electronics here, Mr. Q12, with a second take on the same circuit that I built when I made the movie already, but I discovered I had some problems with the original movie, with the original test, and this is take 2, and it's a little bit hard to make it again, and really I don't like it, but yeah. As you can see here, I'm having 0.9 volts, it means 1 volt almost, and 0.24, it means 240 milliamps. And here 56, 57, and here 908, almost 1 volt. Here is pretty much like there, but this one I'm having a circuit here. So what I'm having here, for those who doesn't know already what I built here, is a tester for transistors, for more specifically for BJT and NPN transistors, but the idea is for BJT in general. And what I'm testing here, I'm testing 3 BJT types of transistors. This BC548, this BD681, and this 2N3773. And you can see them there. And this BC548 is there already under test. And my idea was to find a solution, a much more simple solution than what I was having before. And it occurred to me I can actually put it directly to the power supply, my variable power supply that I'm having it there. And this is what you are seeing here is this transistor is connected directly to variable power supply, to its positive rail and the negative rail. Here I put 1 volt because it generally is working like that at very low voltage. This is the circuit that you are seeing here. This capacitor that I put it is 470 microfarads, is this one that you are seeing it there. But is more, that capacitor is more for the power supply to stabilize it, because without the capacitor the power supply was moving, especially the amperage was moving erratically, at least for my power supply. Probably is you don't need it, but I put it there as more as a precaution, and to be sure that that I will have a stable output from the power supply, and here on the input of the circuit. So pretty much I'm trying to stabilize any kind of fluctuation on my display that I'm having there on my variable power supply. And then the most important thing is that I connected the base of this transistor to the collector, pretty much to the power supply, without any kind of resistance, any kind of protective resistance. And you can probably see here is a link between this middle pin, and you can see the link that is getting out there. I will take out everything and I will show you later. But that transistor is staying exactly as you are seeing it here in the picture, with the collector on that pad there in the middle is the base, and on this right side is the emitter. It's where I'm collecting the ground, and pretty much I linked from here to there with that single link. And also on the capacitor legs, because they are the extremes, I put these 2 wires from this multimeter. Also I am setting it to 2 volts. Here is 2000 millivolts, but it means 2 volts, and I'm reading almost 1 volt, what you're seeing here, 900 millivolts. The mistake that I did last time, I did a couple of mistakes actually. One of the important mistakes that I did last time was the cable. Right now you see that I'm having a very, very thick cable that is going there. This is my secondary cable that I'm using for this power supply. This was the original, the most used cable that I'm usually conducting all my experiments and all my boards I'm supplying with this kind of cable. And I will put it side by side and you'll see the difference. And this is having a much more thicker wire inside. It's important, especially for these bigger transistors. I will drive them to a bit more power. That power, it can and it is actually dissipated in the wires themselves. So that this is a better setup what I'm having here than what I tested before. Probably I will show a little bit of my preview experiments that I did back then, because before everything that you are seeing here, I tried this one and I did promised that I will show the result with what I did from why did I build it, which it turns out that this circuit is most used usually to test power supplies, either this kind of power supply or this kind of power supply that is from ATX, from computers power supplies. And the guy that gave me the circuit, he told me he was actually paid to test power supplies for PCs with this kind of circuitry that you are seeing here. This is called resistor load bank. This is how it's called. And what I'm having here, I'm practically testing the power supplies instead of the component that I was trying to test. So this is very, very complicated way of doing it, and is not even doing it. It's not good for testing a component. If you can test a component with it, but it's not the right way. But I learned some lessons from all these circuits actually. And then the first one was this, which is having this big transistor here, 2N3773. It's written here, is barely readable anymore, but it is this transistor that I'm having it here. And this is an op-amp, LM358. You are seeing it here, and only one op-amp is used from this. This chip is having two op-amps inside it. And this circuit was very, very good for a couple of experiments that I did. This is current source circuit, and I'm keeping the voltage constant, and I'm only varying the current. It's doing pretty much the same thing that this one was doing, but this is better, way more better than that. This is having a lot of issues, a lot of problems to keep in mind, but this is a bit better. Although in essence, it's kind of the same circuit. Both of these circuits are varying the current pretty much from the supply source. And this was good to a point. Actually, I advanced pretty much, quite a lot I advanced with this circuit, and I got some very interesting and very good results with this circuit that I'm having here. It's a very good, and I am highly encouraging everyone to build one. Not exactly like I did it here because it's looking like shit, or because of all these cardboards that you are seeing here, but build it with your own design, with your own circuit boards or whatever, as expensive as you wish. Mine, it was very cheap, that's why I'm using cardboards. And also scrapped radiators here. So this is the circuit, is that simple, and it took me actually a couple of months. It took me probably years, because I built a couple of more circuits in the meantime, and this is the simplest and the most direct circuit. I didn't copy it from anywhere. I imagine it, and most probably more smarter people than me, they already built it somewhere, I don't know, but I didn't find it on internet, I didn't find it anywhere. So this is my contraption, what you're saying here, or my way of trying to solve this mystery of of how much power you can drive through a specific transistor. And this is a modality, this is a way of doing it, and this is my way at least. And if you have an unknown transistor, let's say, you can do this experiment that I'm doing here and compare it with the data from a good transistor that you already have, and you can compare both of them and see and make a judgment how good is one compared with the other, pretty much. So that's one application of this method, experiment that I'm doing here, but it is having more ways of usage, this circuit probably. Also to detect if you have fake transistors, or bad or stressed transistors, electrically stressed, thermically stressed, whatever stress, time stressed. They function a lot, and you want to check it and compare it with something that is brand new and see how good is standing or behaving. And there are many applications to which you want to test a transistor, or many cases, in this world. So this is my way of doing it. Of course, like I said already, I didn't copy it from anywhere. This is from my imagination. I actually built two other circuits, of course in time, and it took me quite some time to make it. This is one of those. This is a current load or current driver, a current limiter, variable current supply, with an op-amp, LM358, you can see it there, and also with a very big transistor here on the back, on a radiator, on an aluminum radiator. And this functioned very well, and I use it actually to collect all this data that you are seeing here. NHS, it means no heatsink power. The power of the transistor without a heatsink, with no heatsink. So when I tested this the first time, all these guys, when I first test them with that circuit there, I got these values that you are seeing them here, 250 milliwatts. That is a watt, is not a volt. For this one, NHS, no heatsink, is 350 milliwatts. I didn't mention here on the paper, but this is at 50 or 55 degrees Celsius. So that's my limit. Of course, you can raise them much more higher than that temperature, but it's not advisable from my point of view. Of course, you must keep them as cool as possible. And this is BD681 at 350 milliwatts. No heatsink for this one, for 2N3773, was 1 watt. So now pretty much I'm repeating the same experiment that I did with this current variator, but this is a bit more direct more from the power supply. It's a bit more risky to do it. You have to carefully fiddle with those potentiometers, and my potentiometers from this specific power supply, you see its name, and it's a series there, STP. From this power supply, those knobs are good for large values, but for very fine values, they are shit, literally shit. They will move, they will change the display. I got a lot of trouble to get to this stable display that you are seeing right now here. So that's why I started with everything powered. As you can see, everything is pretty stable, and it's pretty like on the paper here. Voltage on collector emitter that I took it with this voltmeter. This was another mistake that I did last time, the first in the first video before this one. I didn't took the voltage across the transistor with this multimeter. I was relying exclusively on the display of the power supply, which is pretty close actually to the voltmeter reading, but it's better to do it like this because of the wire that is adding a little bit of resistance into the circuit and is lowering a tiny little bit the actual reading over the component, over the transistor. We really want the wattage over this transistor and not adding the resistance of the wire on something else. We are taking it directly over it. So this is what I'm doing here, and here on the paper I'm taking this value, this voltage over collector emitter VKE. The amperage, I'm actually reading it from there. More correct is to actually add an ampere meter here on this line or that line, and take the amperage in circuit here and not let that one to take the amperage. But again, this is very, very close to reality, because as you can see, this circuit is extremely simplistic. A tiny little bit of resistance there doesn't really matter. So it was good enough, but let's do it by the book. Like my friend, my English from UK friend suggested to do it. Yeah, it's better to do it by the book. And I agree, I was agreeing with him. So I'm taking this amperage, 0.23. From there, it is changing, it is fluctuating a tiny little bit still, but now is way more stable than it was before. So be happy with what you are seeing there and what you are seeing on my paper here. So this 09 times 0.23, let me actually calculate it again for you to see that I'm not lying, is exactly 0.2. So 0.9 times 0.23 equals 0.2007. So that's the wattage that this is a calculated wattage based on these values here. At 54-ish, it is changing a little bit. Probably I should update this temperature here. And I will do it right now. 57. 57. 57 there. And actually it took more than 5 minutes, 20 minutes for this entire experiment while I was talking here. It took 18 minutes on my display here, so it's less than 20. So it's very stable at this point, and that was the wattage last time, and now is a little bit less than that. And it's 56, 57, and that was at 55 last time. So in principle they are very, very close, these two values. Yeah, that's it for this part, and I will test this BD681. And after that, this one. Okay, this is how it's looking, the transistor there. And let me zoom in. BC548, you can see there. So you see how pretty it is. Okay, now I'm having this BD681 connected there. And I already calculated everything. I collected data. So this is what my display is showing, a variable power supply. It is moving a little bit. It's very, very annoying. It's not staying put. The temperature over the component, 67 in this case, and this is the voltage, 1.225 volts. 1.26 I had it in previous measurement with 0.3 amps. It means 0.37 and is very close to that. But here it was at 55 degrees, and here is at 65 degrees Celsius and rising because this fucker is unstable. So yeah, you have to have a lot of patience. So this is a new line for this BD681 here, less than 10 minutes. Oh, 70. Yeah, because that is increasing, that's why I have to bump it, and when I'm disturbing it, it's going nuts. Come on, you see, it's very, very, come on, yeah, there, somewhere there, but it will not stay there. It will either go down or up. Now if I'm blowing a little bit of air, the temperature will decrease and will somewhat stabilize somewhere in the ballpark. This is the data for this specific transistor, but this is actually what we are after, the wattage and the temperature. That's it for this one. Let's do the next one. And for the record, this is how it's looking without the green clamp over it. Okay, I connected this new transistor, the last one, and I connected its base to the case, and the case is the collector, and as you can see here, base to the collector. And so I only connected this two wires from it because the base is connected to the case. 1 volt, 1.3 amps, 58, almost 59. This is the voltage across the transistor. You see, it is starting to show a little bit of more clear difference. 0.7, actually 700 millivolts, so 0.7. And from, yeah, well, 1. It's in the border between 0.9 and 1. It was 1 until now. But now when I'm filming, motherfucker, exactly. Yeah, 0.30. 0.3. I calculated already the voltage is 0.9, and it's very, very close to this one, which again was 55 degrees around there, or probably 60, I don't remember that one, but this is to 60 here, and less than 10 minutes, very slowly is creeping up. But this is it, this is the way you take this kind of measurement. Very simple circuit, very practical, a little bit dangerous. It's dangerous because I connected directly this base to the collector without any protective resistor there. But that's the dangerous part. So you have to be careful with when you dial from very low, easy rising up voltage and the amperage in the same time, slowly but surely, you know, until you get a certain temperature, and then you write it down based on the temperature that you take. You write down all the values that you collected, and that's it. It's that simple. Another very important discussion is that I'm not actually testing all these transistors. I'm not testing them if they are fake or bullshit like that. I don't believe in fakes. me personally, if you got a bad deal, if you really got some fucked up transistors, even fake ones, why not? That's a very big bad luck that you had in the past. I didn't had that kind of bad luck. I actually had a little bit of bad luck with some chips, some analog to digital converters, ADC. They were scrapped and they were sold as new, and I bought them as new, and I believe I requested money back or something like that. I don't remember what I did then. Usually I'm fighting for this kind of stuff if I'm getting bullshit, if I'm receiving what I didn't wanted. But most of the time I'm getting good transistors from both global electronic marketplaces like eBay and AliExpress. They are very, very good and very cheap and very affordable markets. And I didn't get any kind of bullshit. Until now I got only the good stuff. And good enough, I mean, I didn't get the premium transistors, of course. Probably they are some premium ones, but I didn't get those. I got the general, the normal, the normal ones that everybody is using them. And my test that I'm doing here is not for that reason. It's older. The reason is way more older than the idea of having a fake transistor. The idea that I was always having is to test whatever transistor or component I have to find its maximum power that he can run at. So in the past, I was scrapping components, and I have a good selection of components, scrapped components from a lot of diverse boards, especially the old ones, with even germanium transistors that I scrapped a long time. And I didn't have access like it is right now possible with the help of internet and datasheets. But back then I couldn't have an access to these datasheets. I even didn't know they existed, datasheets for each component. I didn't imagine it is possible to have a datasheet. And in my mind, back then, when I didn't have access to any kind of information, in my mind I was thinking how to get a value of how good the component is. And the best idea that I got, that I imagined myself without any kind of help, without any kind of person to discuss this problem, without any kind of electronist or master or whatever guru in electronics was back then. All the masters in electronics, they are all shooting ducks. They were all hunting for goose guns, mice and rats. They were all hunting information. They were uncertain. Everybody that I was asking, they were very, very uncertain, especially for the transistors. Also the integrated circuits, they were just tabula rasa, zero, most of them. And me, myself, with my own logic, with my own discipline, with my own brain, I start to think about it, and I start to realize that probably the most important way to tell one component from the other is the wattage it can support over it. And in my mind, this is a very old idea that I had, at least. In my mind, this case of this transistor and this case of these transistors, and also this case that I'm having here, the package, they are telling you how big wattage they can support, and you can drive through a component like this only by looking on the package size or the package shape. You can see that's 250 milliwatts. This is 350 milliwatts. This one, and this one is 2.75 milliwatts package. Usually, that's my quick and dirty when I'm verifying a component by looking by visual inspection. When I'm seeing this component, I know in the ballpark it's around 300 milliwatts, maybe 400 milliwatts, maybe 500. But those are rare. Usually it's low, and this one as well. This one are even weaker than this 250. They are 100 milliwatts, or even weaker than that, 50 milliwatts. And if you are raising too much power on those 50 milliwatts transistors like this one in this package, they'll burn out very quickly. And that's the reason I'm doing all this experimentation that you are seeing here, and the previous ones that you've seen before with the other circuits. But for now, with this circuit that I'm having here, and hopefully, and I'm very seriously thinking to get another power supply a little bit more better than what I'm having here, without me calculating here. I also find some power supplies that they have 3 lines. This is having only 2 lines, a line for voltage and a line for amperage. But there are power supplies right now already, they appeared with 3 lines, and the third line is with the wattage, and that's extremely beneficial for this kind of experimentation that I'm conducting here. And also, as you can see, I'm having 1, 2, 3 characters or numbers, but the new power supplies, they appeared right now, they have 4. So after 1.6, it will have another decimal here, which is again extremely beneficial for this kind of experiments that I'm doing. So I'm thinking very seriously to buying another power supply next to this one, because it's good to have 2 of them for various experimentation. When you need a second power supply, that I'm actually having it here, this computer power supply, this ATX power supply here, I'm kind of using it, but is in the way, and I don't like it here. So that's my future planning, what to do next. Okay, I also thank you to my friends, even if I didn't get this particular circuit from them, but discussing with my friends about these problems, they actually stopped giving me any kind of answers lately about my many questions, because they are not used with this kind of pushing to the hill way of doing things, but I am used to it. The majority of people, they are not used to pushing to the something heavy off the hill like I'm doing it here. I think I have a tiny little bit of success, and I'm also thanking them, to my friends, that they actually give me some answers, and they point me to in the right direction. Okay, and I also tested in my deleted video MOSFETs, one MOSFET actually. It was this IRFZ44N. This is its data. I tested it exactly with the same circuit that I'm having here, and I didn't realize it. It wasn't my fault at all. I didn't know at that time when a MOSFET is damaged or burned up, but it didn't burn. It was having a very strange way of damage. So it did damage itself, and it wasn't operated normally anymore. And I couldn't catch it. I couldn't figure it out. I didn't see it. And I continued the experiment thinking that he is doing a great job, but actually was what I was having. Let me set it up a little bit. The value on the power supply, because back then I was looking only on the power supply. Let me actually turn it on. So what I was getting on this two actually MOSFETs, they are damaged. They are not actually burnt. They are actually damaged. They have a very strange damage inside them, and I will explain later a little bit. But first, to demonstrate what the error or the damage was behaving while reading my power supply. So my power supply was in short circuit, meaning, and I will do this back and come on, back. So this is what I was getting. This is what I was having all the time. Exactly a short circuit on the drain and source of the MOSFET. And I was getting this value from a certain point. I don't know how to explain it, but I will probably do this experimentation sometime in the future to actually catch when is giving up the MOSFET. So I was dialing it, as you can see. I was dialing the amperage that I'm having here to the maximum. So here, this is the fine adjustment, and this is the coarse adjustment for the amperage here, this line. And as you can see, I'm dialing it directly to the maximum. I have to dial it a little bit less to actually have the maximum here, 5.25. And here was 0.6 or 0.9, a tiny little bit of resistance inside the MOSFET. But basically, this is the value that I was getting it all the time. So I was running it at maximum. So this, it means what I'm having here, 5. What it was, like that. 5.27 actually in the movie I had it. So here is the data for IRFZ44N from the last experiment that I did. And I was very happy actually about it. And I hold it for about 10 minutes in short circuit, my poor power supply there, without even knowing it, without even realize it. So here is the last value at 10 watts, 1.9 volts with 5.27 amps, which is the maximum of this power supply that can give. And the maximum is 10 watts. So in the same time I tested my power supply short circuit scenario, the maximum short circuit scenario. And not for a short time, actually for 10 minutes time. Holy fucking shit. And then I realized after I changed the cable, that is actually, it was actually 3.16 watts. Only by changing the cable with the same setup, I was getting very low wattage. And I was right by changing the cable, especially at higher wattage. That's the problem. You really need that thick cable for higher wattage. If it's very thin, it will behave more like a resistor, and it will heat up. That's what this line here it means. But the idea is that the power supply was in short at maximum of 10 watts. It cannot go higher than 10 watts short. It's a well-designed power supply, very well designed actually. But let's say 5.26. Let me close it because I don't like it running in this mode. So that's what was happening in my deleted movie, and I was pretty pissed off actually because I didn't catch it on time, and I continued explaining, and I was continuing being happy about how strong these MOSFETs are, and in reality I was having a big juicy short circuit on my power supply there. Yeah, shit. That was very ball dropping for me, at least. I got a little bit upset about it. And then after I realized the next morning, actually, in a very quick, very short time, actually, I realized it. I was talking with my friend from UK, from England. He actually also watched that movie as well and give me his opinion. What should I do better with the circuit, meaning adding this voltmeter directly there. And I realized the thickness of the wires. I should change them. These 2 points we were discussed in our chat. And then after I changed these wires, I made a tiny little test. I tried the gate. So this is the MOSFET, how is in the picture here, in the drawing. So the bent leg is the gate here. And this is drain. The straight legs is the drain source. So this is the gate. And I tested the gate to see if it's opening and closing. And it wasn't. So this is the error. This is the damage. This is again, this is a very strange damage that I never seen it. I never encountered it. I believe I encountered it in repair movies from YouTube, from other people that are repairing boards, you know, circuit boards that are containing MOSFETs on them. And in most of the cases, they say it's a burned MOSFET, but like me here, they are also unsure when they are saying it's burned, because it is not actually burned. When it's burned, it's not conducting anything. And also is showing, usually it's showing a little blip or a mark of burning, of bursting. But this is perfectly fine visually. But let's say it's exclusively internally. So, and it appears to be exclusively internally there inside it. It's actually a type of damage of the MOSFET. This damage is behaving like this. If I'm switching the gate of the MOSFET, it should switch. It should allow a current getting into the drain and getting out from the source. This is the control pin, the gate, and it should stop or play these two pins. This was not happening anymore in both of them. So when I tested this gate pin to see if it's switching, after I see that it didn't switch shit, it was actually conducting through drain and source unaffected, or it didn't matter if the gate was activated or not activated. So it was unaffected by the gate signal. If I'm putting right now a positive and negative through these two pins, it will also show a short here. Actually, I can do this experiment right now to actually show you exactly the error, exactly like I showed you here with my tweezer. I've connected it like this, you see, positive on the drain and negative on the source pin, and the gate is floating, literally floating, and there is, yeah, it's jumping a little bit. I have to back it up a little bit. There, 526 at 0.8, like I told you. And it is getting warm, well, hot, up to 88 degrees Celsius, something like that. And I will close it. So this is the damage that I couldn't catch it. I literally couldn't catch it. And unfortunately, my friend did the same experiment. My UK friend did the same experiment and said, oh no, everything is all right on his side. Everything is by the book, by the data sheet. And after he did his experiment, I discovered that this motherfucker was actually burned. I told him, sorry, lad, but it appears if my MOSFET is burned, probably yours is burned as well. And he didn't say anything after that. Then, after I discovered that this phenomenon, this error, this damage, specific, very strange damage of the first MOSFET, the one that I was always testing all the time. This is number one. Then I inserted a brand new one. This is number two, and I wanted to verify if this failed from prolonged exposure. In my mind, if I'm making a short experiment, a short timed experiment, usually the components that I'm used to do my experiments, especially BJTs, this guy here, these BJTs, they don't burn instantaneously. They take a little bit of heat first. They heat up to a certain temperature, and then they decide to burn something. But they give me a very clear sign before they are burning. They are not dying just like that. Like, you know, this is a instantaneous death of the MOSFET, and I'm not used to it. Literally, I'm not used to it. And probably many people are not used to it until I'm exposing it here. So I hope this will help some people out there. Then I tested this number two, like I said, and what I did, I also tested it for the voltage on the gate. And I believe I lowered everything. I lowered the voltage. I don't remember what I did exactly with this, but I was trying to test at very short timing because this was functioning, this was conducting for literally hours at very high power, at very high temperatures. And I said, well, this is just weakened, and because of the weakness, too higher temperature over it, too higher current, too higher power dissipated on it, and it just give up. Because of that, I didn't imagine it was instantaneously. I didn't want to believe it was instantaneous. So that's why I came in with this second one, relatively at the same parameters, at the same parameters that I was having for the first one, with this amperage to the maximum, everything like it was before. But this time I was just making a very short connection to see what is happening, and I believe I even give it back like on the middle here on the 2.5 amps. I believe I was giving it. So in the maximum is 5 amps, and in the middle is 2 point something amps, and just, you know, not to give it full power. And it also got burned. And after I made the test, I checked immediately. I checked the responsive of the gate, if it's switching the drain and source, and it didn't. The drain and source was also shorted inside. And exactly like my tweezer here. And the tweezer, this is called the tweezer effect, when it's shorting inside, you know. And very, I'm very unhappy about it. And then I took a third MOSFET that I didn't burn it, and the next idea to test was if because I was testing it. This is the stud. I'm actually having it here, and I can actually show you. So I didn't mention this, but I will mention now. I put 12 volts from this power supply, from this ATX power supply from a PC, 12 volts here, and this is 0 volts line. And on the gate is 12 volts to command these two pins to make them on off. And when I'm powering from here, the entire power supply actually, you see, now is on, and now I'm putting that 12 volts on the gate and is opening those two pins to pass current through them. And when I'm plugging it out, the entire power supply and this 12 volts here is shutting off those two pins. That's the idea. And I tested it, this MOSFET that is also brand new, I tested it with 5 volts from this variable power supply, and I tested it if it's working, because I was starting to think maybe they are already damaged, that I received some fucked up MOSFETs, but it wasn't the case, and it was working fine, it was switching fine. And then I said, well, I did this experiment before and it worked with 10 and even with 20 volts on the gate, to command the gate with 20 volts. So it's not actually the signal wire that is coming on the gate, because this was the next idea. Actually, this was the immediate thought that I had. I thought I burned the gate, and that's why it's making this short inside. But it turns out it's not actually the gate problem. And then I power it here with 12 volts from this wire, signal wire, and that one. But here on the drain and source pin, I put way less current, and I can exemplify it right now. I can show you, but let me. So now I'm powering it, but let me bring way down. If I remember, I put it on 1 volt here. Okay, I cleaned up a little bit, and I put these two alligators. I actually connected them, as you can see. Yeah, it's moving a little bit. So right now, if I'm not powering the gate, nothing is switched there. And when I'm doing this, is 0.06, it means 60 milliamps. If I'm powering it off, now it's switched back to the voltage. You see, it's switched here as well. I switch off the gate by interrupting the 12 volts here. And now if I'm putting it again, if I'm connecting it again, just because, it's showing 007, I'm shutting it off, and then is switching there. And this is how this is showing that it is commanded. But as you can see, I lowered everything to the minimum here, especially the amperage and also the voltage, both of them, just to be on the safe side. And this is how it should perform. This is how it should work. So this is working correctly here. But these guys, both of them are busted. And another mistake that I did, and this was a genius sketch of my English friend, because he is a genius, and I totally didn't say it myself. Sometimes you can see this on other circuit schematics on the internet even, and I did learn it from internet as well, of course, like everybody else. You put 10 kilo here to actively close it when you take out the positive. You are shorting the gate to ground to close the MOSFET, to close its drain and the source through this active pull down resistor. But you also put a protection, a high current protection resistor here. And from what I remember, the logic of it is anti-spikes, too much higher voltage, because the voltage is too high. By limiting its current through this adjacent 10 kilo here, it is protecting a little bit more better the gate and the MOSFET itself, not to get damaged by that spike, from what I remember. But probably it was another reason for this adjacent resistor here. But I put it anyway, as you can see it here, from this bent leg, which is the gate, to the negative rail. And my genius friend from England, because he is a genius at this particular setup that I'm having it here, I didn't catch it. I do know these things, but that's why it's good another eye from exterior to watch what you are doing and to point out the little shitty mistakes that you are doing it without thinking sometimes. This is actually a voltage divider here, 10 kilo and 10 kilo. And if I'm putting here 12 volts, I will collect here on the gate 6 volts. And in this setup that I'm having it here, I'm not actually conducting it correctly. I'm not saturating fully the MOSFET, and it is acting a little bit like a resistor, a tiny little bit. But it's fine for what I wanted to present and to demonstrate. It is fine as it is here, but it's not really totally correct. Probably a better setup to have here a protective resistor. It should be to have it at 100 kilo, either here or either here, and the voltage divider will not be half of this voltage. It will be 0.3, I believe, or something like that. So it'll here it will be something like 9 volts instead of 12, something like that, you know. a little bit better than it is, but it will remain protected theoretically. I'm not completely sure. Probably this is more like this is from the BJT way of protection is coming. It's just a memory muscle that it remained with some people, including me, most probably. I am inclined to add this extra protection here just because, you know, anti-spikes, anti-high current, whatever it is, just to give an extra, a tiny little bit of extra protection in case, you know, it's better with it than without it, in my mind at least. So that's a little bit of a parenthesis here. All right. So when you are building your circuits, it is better to remember this little detail that it will interfere with your expectations. You are expecting something out from this transistor, but you did this extra protection here, and you disturb the balance of the force here, and you change the actual voltage on the gate. And this is a little gotcha. You know, I gotcha, and this is a little mistake that everybody can make it, especially in design time. And it's very important to keep an eye on it and to be aware of this little details, like this voltage divider thingy. That in this case is a problem and not a helper. It's not help because you want this full 12 volts here, and not only a little bit of this 12 volts or a part of it. That's it. So again, this is a very, very strange damage. What I did here, it proves how it should actually work at very limited power through drain and source. So the drain and source is the problem. You have to limit the power to a certain value. I'm not sure exactly what that value is or the temperature it should tell me. Usually when I'm testing this BJT NPNs that I just showed, it's telling me that it's giving up by raising its temperature, and I'm collecting the temperature with my thermometer here, as you've seen with my green clamp here, alligator, and that is how I'm telling when it's close to giving up. If I'm exaggerating, of course, but I didn't exaggerate. I only got to the 50 degrees Celsius, and then I decided it's hot enough, so I collected the wattage over it. But in this case, it's apparently, for the moment, I don't know what to say. I cannot get a correct temperature over it. It's not even raising to 55 degrees. It's raising up to, I believe, 40 degrees Celsius. And most probably at that temperature is already giving up. Is already made that short inside, and is already dead. So that's the problem. I cannot catch when it's giving up by the temperature itself. I believe it is possible to catch with the thermometer, but I have to make more aggressive tests. And I am already thinking on a way of doing it. I already have a solution in my mind how to do it. Okay, and this is the circuit that I used. I put a negative common with this other negative. As you can see here, the negative wire from this power supply is common with the negative wire from my variable power supply that I'm having there. That's what I'm showing here, this wire. And a separate power supply, this 12 volts from my PSU number 2. And this is power supply number 1 from variable power supply here. And as you can see, I even noted it 1.9 volts it was showing at 5.27 amps, the maximum. And I was very, very happy that it's conducting all this power. And then I thought to myself, maybe this is too good to be true. And I checked everything, and it turned out it was fucking burned or welded inside. The tweezer phenomenon. It's shorted. So this is the capacitor here. It's the same setup like I was having it before, like here with this capacitor there. But instead of that, I was having the MOSFET, and pretty much the same thing. The only difference is this secondary power supply with this 12 volts on the gate to drive it hard, and from 10 volts up to 20 volts. For this particular MOSFET is 20 volts, but usually people are telling me 10 volts is enough to bring it into saturation mode and not behave like a resistor. Because you are not giving it its required voltage here on the gate, it will behave more like a resistor, and it will heat up very hard and very quickly, and it will not conduct too much current as compared when you are giving it the correct voltage, 10 or even greater than 10 volts on the gate, and it will conduct a lot of current at lower power dissipation over the MOSFET. So it will stay cold for a very high power conduction through it. So that's the circuit, that's the problem, and that's it about it. Yeah. Very, very shitty problem. It put me in the situation of making this second movie, and it's not nice. All right, that's it. Thank you very much for watching, and I hope you like all my experiments. And I say you goodbye from your favorite electronist here, Mr. Q12. Bye bye.